Good afternoon, everyone. Welcome to today's National CyberWatch Center webcast. As a courtesy to others, we ask that you keep your microphone muted during the presentation. If you're using an audio-only connection on your phone, you can press *6 to mute and unmute. Today, Dr. David DeMaris will be presenting machine learning, computing as signal, and security. David has more than 30 years of experience across technologies, including very large-scale integration design, design optimization, software, machine learning, and advanced semiconductor processes. He is an innovator in the application of signal processing and machine learning techniques in semiconductor design and process integration, and holds several patents in this arena. His Ph.D. research, spanning neural network and computational neuroscience, focused on recurrent networks with time-varying coupling applied to task and visual psychology and computer vision. His graduate work in cognitive science, linguistics, neuroscience, and biosignal analysis led him to recently work in expressive robotics and natural language dialogue. He's also an active musician and sound designer, and in 2014 created an opera based on historical characters in physics and psychology. Please welcome David DeMaris. David, we're looking forward to hearing from you today.
Hear me?
Yes, you're unmuted.
And are you going to unshare?
I'm unsharing. Both hands are going at once. There you go. It's all yours.
All right.
Very good. We've got you. You're good to go.
Okay. Well, hi, everybody. That was a great introduction, I guess, because I wrote it. I'll say that, I would primarily think of myself as somebody who's worked more in applied research, technology transfer, and I've been doing that for a while. And in particular, some of the techniques that we'll talk about here are things that I did maybe 20 years ago, and well, not quite 20, but 15 in the semiconductor world. And now there's actually a government program dishing out grants to do that kind of work. So I feel kind of okay about that. So what we're going to try to do today is give you a qualitative overview of machine learning. It's a very mathematical topic. We're not going to look at a lot of math, but just give you some of the basic ideas, including this concept of features or measurements, and how you have a distance between some objects that you're measuring. We'll talk about the types of learning. There are more than the big two here, and there's combinations, but we'll hope to touch on those. And a few topics called dimensionality reduction, and a sort of similar idea called similarity hashing. We'll talk a little bit about pitfalls in machine learning, and why hasn't it taken over the world yet, especially in cybersecurity. So having gone through that, we'll look a little bit at how you turn the traces of activity on a computing and networking system into a signal and try to make sense out of it in the cybersecurity setting. And finally, we'll look at a couple of examples of what things that people are doing recently and ways that you can kind of attack the machine learning system itself. So first of all, let's just ask ourselves, what kind of problems is machine learning being used to solve? So in a very abstract way, if we say we've got a set of one or more measurements, we want to answer questions like, okay, if we know X, what is X going to be at some future time? If we know a couple of variables, X and Y, and we know X, what is Y going to be? We might ask something like, we've got some data, some measurements about X, and we want to know what category of thing is this, or what class is it in? And if we have many such X's, maybe we just we can just kind of explore a cloud of data and find the categories, even if we don't really know what they are. I recently read a paper where psychologists have talked about personality types that they basically just created out of thin air, but they were able to take a long list of traits that they measured and say, oh, now we actually have used machine learning or data science to kind of discover some personality types that make sense mathematically. You may have also heard about things like, chess and backgammon and Go being solved by games and video games. So you're able to sort of look at the frames in a video game and say, okay, what's my next best move? So it's been very successful. In cybersecurity, what are the kinds of questions that you might want machine learning to solve for you? So if we've got a file, virus sniffer or something is looking through your file system and saying, hey, does this contain malware? You might want to ask, is malware running on my system, or is it behaving normally? You might want to say, am I leaking information to the outside world that I shouldn't be leaking? Is there anything sort of unusual going on in terms of the network activity? Is there an intruder or maybe an insider doing something weird that's not part of the normal system workload? So we could say, hey, is somebody stealing our compute resource to mine crypto, for example, or whatever else they want to do? Maybe you're building software and you want to understand whether something about your build process has been compromised so that you're then distributing bad software out to the world. So we're hearing a lot about machine learning the last few years. And what's going on? Well, the big breakthroughs starting around 2010 are the data that's available harvested from the web, like something called ImageNet, for example, was a big breakthrough. And what's really happening there is everybody's sort of working on the same problem, so you can really kind of understand what works and what doesn't. And we're able to kind of scale the labeling of data, which is necessary for some kind of machine learnings by, either volunteers doing it or paying people a little bit to label images or any kind of data. So the other thing that's going on is that we have, ever increasing compute power, and we've got GPUs, maybe originally created mainly for gaming and video processing, but now they're being used for all kinds of scientific computing, and we have libraries like TensorFlow from Google that are designed to use those efficiently. We're also able to kind of drink in data from the whole web at once using some software technologies like Hadoop and Spark. And finally, there have been some algorithmic breakthroughs, in particular, the sort of flavor of deep learning, something called convolutional networks, which is important because rather than people making decisions about what's important to look at, they kind of discover what's important in the data from the data itself. There have also been some interesting breakthroughs in terms of word meaning, also using these similar kind of machine learning techniques. So, all right, so let's start to really dive in. So we'll look first at features. But before we do that, we're going to look at an overview of the whole field in a kind of tree structure. So at the top of this tree, we could say machine learning, or we could say data science, statistical inference. There are many things, but I labeled it this time data science, and this covers most of what's here. But so you have different types of learning. So supervised learning is the one that we'll probably hear the most about. And there are several different types, not of all of which we're going to visit too much today, but I just wanted to put them up here. And the kind of new exciting stuff is down at the bottom, certain kinds of networks called deep learning, adversarial networks, and recurrent networks. And we will show those a little bit. There's also some things called unsupervised learning, which is something where you're kind of trying to discover some structure in the data without specifically having to label it and go through a big training process. And that is closely related to something called dimensionality reduction, which is just some mathematical techniques that are used everywhere in this world for various reasons. Finally, we're not going to talk much about it today, but you might find people doing things in the cybersecurity space with what's called evolutionary computing or genetic algorithms. And then over on the right, I've got signal processing, because there's an entire world that's really coming from electrical engineering primarily, where there are a lot of techniques that aren't, conventionally machine learning, but they are sort of used to train classifiers and do classification. Okay, so before machine learning was really a thing, there was just statistics, which is a course that you might take at some point, and maybe even in a geometry class, you would look at example problems where you're looking at, plotting one variable against another. So it's all about studying the relationships between measurements. And often you would see this because you're trying to support some hypothesis, like smoking causes cancer. And people in engineering and science would call this curve fitting. So you would just try to somehow come up with a straight line or some kind of curve that really cuts through the data points. And if you look at the distance from every point to the nearest point on the line, you could say that's the error for that point. And if you add up the error for all of the points, that's what you're really trying to minimize to get a good model or a good curve fit. So as we kind of move into the other types of learning, let's just talk a little bit about observations and features and vectors. So I've made up an example here that should work for students. And I'm going to say, like, suppose that we would actually like to predict the grade that you're going to get as a student, and we have various data or measurements about you. So and this table, we've got the student on the left. So I've got 3 students. One's getting an A, one's getting a B, and one's getting a C. They're taking different numbers of courses. They're spending more or less time studying. Sometimes they have jobs. Maybe we don't know if they have a job or not. But we look at how many roommates they have, which maybe is a distraction, or maybe it's a helper if they're in the same major. You wouldn't think it would make any difference what month they're born. I think I put one of them in December, so maybe their birthday is on the day that they take the final, and that makes it a little hard. And hey, do they spend 20 hours a week gaming or 0 hours a week gaming? So these are the kinds of things that we talk about. And some of these fields or columns you can see are numeric data. And some are, if it's text, we'll usually call that categorical data. Okay, so if we have some data like this, the first thing that you usually do if you're going to do machine learning of any kind is what's called pre-processing or cleaning the data. So part of it is because these numbers all maybe vary widely. They don't vary so widely here, but it could be much worse. You do what's called normalizing, or sort of putting them all into the same scale so that they all, say, range from 0 to 1. And you may also go through, you can see that in the first one, I have, even though I didn't know about working, I took the average of the 2 other values, which is the thing that you might do in terms of cleaning up your data. So now, having done all this cleaning up, you can say, all right, we're going to call this a vector, and we can now train what's called a supervised model for this. But one of the things that you need to take into account is that you may, if you have some value that's just a little bit odd. So student 3 is the only person that got an A. They must be a genius because they're really taking a lot of load. They don't ever study, and somehow they still get an A. So if we include them in the data, we may actually get kind of a distorted model. So it's kind of typical that before doing some kind of training, you may actually remove outliers. So I've highlighted that in red. Okay, so if you think of each one of those rows, typically what machine learning is going to be about is thinking of a point in a space of features. And the easiest way to understand it is if you think of only two. So you have two axes, X and Y, and you may remember in a trig class, you could say, what's the hypothesis of the triangle is a squared plus b squared is c squared. And that's also the distance between points A and B. So if we think of every column in our data that we're looking at as a dimension, then this is the math of this talk is to basically say we can actually compute the distance between points in any number of dimensions, n dimensions here, by kind of going through a loop and taking each one of these distances between any two corresponding dimensions into points or two observations, two students in our example, and we take the square root of all of that. And this concept of distance sort of underlies almost everything in machine learning, and there are many ways of measuring distance. This is sort of the most common and somehow maybe the most primitive one. But okay, so we're kind of returning to this topic that we talked about, regression, where we're often trying to predict one value from another. We're going to predict a model value from inputs, and maybe want to predict a value at a certain point of time. We may want to do something like say, what is the next probable event or the most probable next word that a person is going to speak? And I think I showed on that first chart that usually when you're building a model like this, it somehow comes down to minimizing the distance or the error. I'm just going to throw out that a lot of the interest lately is in something called recurrent networks for prediction, especially when it comes to language and speech recognition, that kind of thing. But, okay, so regression is about prediction. Classification is about saying, like, I've got some observation, some data point, one of these students, and I want to know if it's in one of n classes. Sometimes it could just be two classes. There's a sort of famous episode of Silicon Valley where they decide whether something is a hot dog or not. In the context of cybersecurity, we might have a file and we want to say, hey, is this malware or not? Is there an intrusion in progress or not? Okay, so from looking at these measurements, we have to decide which class is it in. There's two big families of methods for doing that. We won't dive in too much, but I'm just sort of throwing it out to say one is discriminatory, and somehow in this, you know, this cloud of points, the measurements that we have, we want to find a boundary that separates the classes, the passing from the failing students, for example. And the generative mode is somehow, rather than have one big model, every class gets its own model based on these measurements. And then we want to say something like, which of these classes gives the strongest response? And so some of the neural networks and deep learning are a little bit more in this mode, but it's not the only way. Okay, so just to kind of revisit this one more time, I'm going to go back to this class example. I'm going to say, remember we're trying to guess which grade a student is in, and let's suppose it's just pass or fail in the simple case, and suppose that everything turns out to be kind of random except for how many hours you take and how many hours you play gaming. So I've kind of plotted these on two axes and drawn a line in the middle on the left side that says, hey, okay, everything above this line is failing, everything below this line is passing. On the right, I've made like a little bit more, this wiggly line is a kind of more detailed model. It's a more complex model. And you might think that's somehow better, but not necessarily. It depends on many things. And that's a kind of still a very deep and difficult area in machine learning that's generally called, getting a good fit for a model. Okay, so I think I'm going to just mention again so we had the discriminative and we had the generative categories of models. So on the right of the little cartoon here, we're just showing that for a generative model, maybe you have some sort of formula that draws an ellipse and says all the points in this ellipse centered at some point are covered by this particular model. So, so every class has its own set of functions or something rather than just a boundary. But I think I just wanted to make the point that there are things that can be more elaborate, like there's some methods around that really try to generate objects as part of the process by basically create a dictionary that you can use to create objects. So there's a technique called dictionary learning for that. There's something that's getting a lot of attention these days called generative networks, where you, for example, generate images, try to determine whether they're fake or real, and then you go on to recognize things out in the real world once you're able to solve that problem. Okay, so we've kind of danced around this, so I want to finally just revisit one more time the big categories of learning. So there's supervised learning, where you have to have class labels, which may be expensive to get that. And typically you split the data you have into a training set and a test set. There are some ways to do that multiple times to improve the accuracy of your model. And you can also use subsets of features. Sometimes having too much data gives some problems called overfitting. We'll talk about a little bit. So it could be that you don't actually know the classes, and this is what we call unsupervised learning. The sort of oldest and most widely used of these things is called clustering. There are also a family of methods called dimensionality reduction that we'll look at coming up. Okay, so clustering basically says we've got points in some number of dimensions, and usually we look at 2 dimensions just because that's what we can easily visualize or grasp. So here a cluster is kind of a circle around a set of points that seem to have some separation from everything else. Now, it's not guaranteed that this is what your data looks like. Your data could be sort of randomly filling the space, and then the idea of clustering doesn't work so well. There's a lot of fancy math that can be brought into play to kind of warp the distances so that maybe some less obvious structure pops out. And we're going to look at that in a second. But a point to make here is that sometimes what you're really trying to do is find the things that do not fit a pattern. So they're a bit distant from the rest. Those are generally called outliers. And particularly in security, you'll hear the term anomaly detection a lot, which basically says we want to find these outliers. In fact, maybe what we would like to do is just try to train a system or discover what is normal in the computing and the network behavior, and just call that the normal class, and then sort of be watching for activity that is an outlier, that is outside the normal behavior. Okay. All right, so we have mentioned a thing called dimensionality reduction. And so how does it play in? Well, there are a couple of big reasons for this. One is the speed of learning and supervised learning kind of depends to some extent on how much data you have and how many columns of data or how many features that you have. And not only the speed that it runs, but also the quality of the model can in some cases be better if you have fewer features. So one of the big ideas of dimensionality reduction is to kind of pretend that there are fewer features than you originally started with. And really, this is called projecting into another space. So if you're presenting your paper, your algorithm or something, and it has many dimensions, yeah, we can handle 3 pretty well, but it's very typical that you show your data in 2 dimensions to fit on a page or a screen. So just in general, people have been using this for, maybe a century for some of these old methods. Something called principal components is the most common. The great thing about it is that it tends to preserve the structure of the distances in your original data, both locally and globally. So there's kind of newer methods that are called nonlinear methods, and I think there's many of them are called manifold learning. So in this case, they tend to favor the preservation or highlighting of local distance between sort of near neighbors in space. And I've just thrown a couple of these up. And this one was from 2018, and we're actually comparing 2 different dimensionality reduction algorithms. The colorful little clouds up on the top are the numeric digits 1 through 10. And the point that they're trying to make is that this in the center, these similar, we would probably agree that 4, 7, and 9 are somewhat similar to each other compared to 3, 5, and 8. Those are more easily confusable. And so these guys are making a point that their algorithm for doing dimension reduction separates those more than the one on the right. And that's useful. Okay. So I'm going to just try to summarize what a supervised learning workflow looks like now. So we talked about cleaning. So there we're dealing with maybe stripping out outliers, handling missing values, feature extraction. Somehow we have to decide what of the data we're using, and often we go through this dimensionality reduction operation. Now we have some sort of training on subsets of the data, and this is often sort of looping around and kind of shuffling the data. And finally at the end, on the right, we have a model, and we're going to test that on some data that we left out of our original set. If we're happy with that, we may go back and sort of experiment more, change parameters. But let's say it looks pretty good, then we're going to deploy it on the bottom. And you really have almost the same sort of workflow or pipeline where you clean the data, do the feature extraction, and then you sort of run this through the model and do your prediction or classification and take some action. So if it's cybersecurity, this is when you get the call at night going, hey, anomaly detection, there may be an intruder on the system. Okay, so when you do all that stuff, why is it still hard? What kind of things can go wrong? Well, we gave a very simple example of cleaning data, but in general, that's maybe hard and expensive, and it's not obvious what the right answer is. But if you throw out a lot of data because it's, quote, dirty, then maybe you don't have enough to train your model. Okay, so this topic of feature selection and dimensionality reduction is not completely obvious. There are a lot of methods to do it, but it turns out that a lot of features were just kind of wrong, or we're getting much better results since we stopped letting people decide what the features were and let the machine discover them themselves. So some of the methods that are pretty hot lately do what we might call adaptive feature discovery. All right, so too many features and not enough data can actually result in this problem called overfitting. which basically says that you've trained on some data, but when you show it to the rest of the world, you get really a lot of false positives saying like, this is an attack, but in fact, it's not. And as I mentioned, there are techniques that try to help with this, but it's kind of one of the biggest classical problems with machine learning. There are some ways, techniques that have been developed to specifically help with this problem, and I'm not going to dive into these there, but I'm just going to, they'll be on the record as things that you can go off and look about, and they're usually available in all of the machine learning packages you might play with. Okay, so having done this process, how do we actually measure the performance in terms of the quality? Like, is it doing a good job of discriminating things into classes? This is primarily oriented towards supervised learning. So up at the top, I've got a little table that says, like, let's talk about an alarm situation. So we want to say, well, we predicted that there's an attack going on, and either there is or is not. So if there is not, we're going to say that's true negative. If there is, if we predict an attack and there's no attack, then that's a false positive. So if we predict an attack and there is an attack, that's true positive. Similarly, if we say there's no attack going on, but there is, that's true negative. I'm sorry, yeah. And if we say there's an attack going on, and there's not, we can say false negative. All right. I feel like I did not say that perfectly. Sorry. So there are several different quality measurements that you can define that use various combinations of these things. And depending on what you're trying to do, one or the other may be more appropriate. Normally in machine learning, particularly in cybersecurity, probably the biggest problem is false positives. So you get too many warnings of attacks in progress, and what are you going to do? It's hard to look at all of them. So you may be able to adjust something about the distance or some kind of threshold that says, hey, I don't care if the outlier is kind of closer to the cluster of normal, then don't tell me about it. But in general, these measurements can sort of bias towards either false positive or false negatives, all right? I'm going to just give you a really quick look at deep learning because I think everybody's probably heard about it. This is sort of showing how in the context of images, you take something in and you do what's called convolution, and you get really like a set of different kind of distorted pictures, and then you tend to make a smaller picture, what's called subsampling or pooling, based on little patches of the image, and you repeat this process, more convolution, more pooling, and at the end you have a classifier that tells you what kind of category that you have. The key thing about this is that the features are discovered from the world that you show it, a very large set of images or something, rather than engineers deciding what the features are. Another big hot family of networks are called recurrent networks. It's shown over on the left. And the one that we just looked at, deep learning, the data always goes input to output and always flows to the right. And the distinction with recurrent networks is you see those arrows that sort of loop back. This is sort of the definition of recurrent, is that there's feedback in the system. And the thing that is sort of getting most of the attention these days is something called long short-term memory networks. And kind of the key thing about them is that they have some sort of extra memory control inside each one of those looping feedback areas that allows them to forget things based on a training signal and whether it looks like this particular input is useful or not. All right, So that was drinking from the fire hose. I'll just sort of stand back and say, what do you really need to know about this? So if you're not really a researcher who's trying to make your name and advancing the state of the art, there are really a lot of good toolkits out there that you can use, and you don't have to write your own. Many of them are free. So I've mentioned a few here. But the thing is, it's an art. You still probably need some training to figure out which problem is, or which method really applies to the problem you have. And going through the training process is a bit challenging still, right? But I think people are always working to try to make these things more automatic. Just to give you an example of choosing the methods based on your problem, like if you have so-called categorical data, like text data, then methods like random forests are good at handling that sort of thing and making a decision. If you have a sequence with some time dependencies, then there are other methods here, and I'm just going to kind of breeze through this stuff a little bit faster based on the time here. So you probably heard of big data, and I just want to make the point that some of these systems are, say, Python scientific learning is pretty good for small data, but if you're really trying to look at vast logs in a big enterprise server farm, you probably need big data processing, and these are the kinds of software systems that people use for just getting the data into shape, maybe doing data cleaning, but there is also support for machine learning across big farms, particularly with the second one here, Apache Spark. They have their own machine learning library. In the security world, a very popular and longstanding product called Splunk was really originally created as a kind of searching your log files. So, and I hope everyone knows what log files are. Basically, just if you're running Linux or Windows, and if you enable it, you're able to write out a certain amount of data. So, kind of tracing the system calls, programs that are being called, maybe network activity. So this general field is called log app analytics, and the recent versions of Splunk have tried to sort of build some machine learning in here, and they're also going to try to help you kind of understand, based on a big category of problems that you have, what is the right technique. So this is just kind of their example page for how you can use some of the things that are now available within the Splunk world. All right. So I'm going to kind of shift into the second topic, computing a signal. So what do I mean by signal compared to other data? Well, we looked at how you can do machine learning with just tables of data or observations. And so we've called those features, right? So, but for many processes or object, there really are some kind of expected patterns in time and space. There's a process that's going on, it's not random. So this is a definition that I just made up. So I said a set of values in time or space with non-random relationships between neighboring elements. In the example that we looked at, it's not clear that like one of these fields, like number of study hours gaming, may have something to do with jobs, but they're really a little bit randomly related. So in this case, example signals. So on the left, we've got music, an audio waveform. On the right, we have an image. And below, we have a text stream, okay? So I guess just talking about the image a little bit, it's like if we see eyes, we can kind of expect that there's probably going to be a nose in the picture somewhere. All right. So let's come back to computing and sort of think about what are the signals that we have here. So in both the execution of processes and networking, really a lot of possible traces. They all kind of look a little bit more like natively like language sequences, which maybe could be one type of signal. So we've got our system logs, system of sequences of instructions that are being executed by a program, which you can trace, although that's pretty expensive to store that. Maybe we have something logging about where we're touching the file system, where we're accessing a database. If we have some kind of server that has a gateway to the world and it's fielding requests, we can probably turn on logging there. So the way that people often treat signals in engineering is that they try to say, if we have something that's changing over time, like an audio signal, we try to break it down into some components that we can then measure. Some of you may have heard something about like the Fourier transform. It's a very famous thing that you do in audio processing that gives you like low frequencies and high frequencies. And over on the right, I'm trying to show you that eventually you can basically have a vector of numbers that describe what happened over some window of time. And in a paper that we'll look at later, we'll see that people actually look at the time between events in a log, and they can kind of create this time series or a waveform basically by looking at the time between when particular events happen that are really a kind of categorical data, like this program was run, this system call was run, this networking thing happened. So let's just focus on networking a little bit. In the networking world, you've got packet level filtering and logging resources. For a big server, that's also very expensive. Maybe you could sort of randomly capture things, or maybe you have a sort of programmable firewall that maybe filters out a lot of things that are sort of obvious known attacks. So you've got a reasonable amount of data to deal with. So once again, we've got like packet types, ports, things having to do with the transport layer. You may be concerned about other things like, are you giving good service to whatever your server is trying to do, and you're doing logging for that, as well as for security purposes. You can look at the name server logs, the DNS server logs. If your server is doing software as a service, then maybe you have some sort of API and these sort of famous protocols like SOAP or REST, and you can kind of turn on some logging and look at these requests and consider that a kind of signal. This slide is from a conference called Knowledge Data Discovery. They had a competition to kind of detect anomalous activity on the system or intrusion activity, and this was a list of the features that they used. I will just let you kind of observe it for a minute. But you'll notice that some of them they called discrete. That's what we called categorical before. And then some of them are more numeric. They're looking at some things like how many connections happen in some time window, like every 2 seconds. So that's something that if you plotted every 2 seconds, you would basically be having a time series or a waveform looking object that you could do signal processing on. All right, now I've got, just gonna dive in with the last 5 minutes or so here for a couple of examples. And I went out and looked at some papers. Surprise, here's the thing that you really haven't heard anything about other than I put it up there as, this is kind of related to this idea of dimensionality reduction. So people are using something called fuzzy hashing. So hashing is a computer science topic that's in one way or another it's kind of mapping one digital object onto another. So you may have heard of crypto hashes, which are, say, take a unique signature of some long string, like a program, and you can determine then, did somebody modify this, during the download, or since it was put in the database. And you can also use this hash string to say, like, do I have an exact match? Sort of more common thing is
what I'll call an index hash. And you're basically taking a text or a number and you turn it into a smaller number for fast lookup. The example that's given here is a phone book. And what I want to point out is if you look at the strings or the keys, the names of the people, some of these names are pretty similar. Like the first two, their names, you know, half of the characters are Smith. So those are actually kind of similar names, but where they wind up in a table is kind of random, and that's by design. You really want, what people mostly wanted in a hash function was to have a kind of equal distribution so that every number in whatever the range is gets used, because ultimately you're going to look them up, and if they map to the same number, then you have to kind of run a search on every one, and that's slow. So the main idea was fast lookup with indexing. So a thing that people noticed at some point is that, okay, on the left, there's this idea of hashing that we just looked at. And if things are some way close together, like those names, or I had the quick brown fox jumping or the quick brown fox running, we would probably say those are similar. We can just change a few characters to turn one into the other, but they're going to wind up hashing a bit randomly into space. So a field called locality sensitive hashing or similarity preserving hashing was invented to do this. And I'm just going to point out that this kind of has a family resemblance to dimensionality reduction, but it tends to not really use the ideas of points in space. There's some kind of trick about how you manipulate the data that gives this property. But like dimensionality reduction, it is not a supervised process. It doesn't really require training or examples. Now, you can often show a lot of examples to get this, but it's possible that you have a function that doesn't require training at least. So here I'm just sort of pointing out these guys tried this technique and reviewed what had happened before, and they said, oh, well, there are actually some big problems, but we have solved it, and the way we did it is by coming up with a better distance function that is symmetric when you compare two things. So if you say A is similar to B, you should also be able to say B is similar to A, and apparently that wasn't always the case. Here's another example of what people are doing with deep learning that we very briefly looked at, and they're using this. It's both deep because there's many layers, but it's also the LSTM that we mentioned, which is typically used for patterns with a kind of time behavior. And one thing I really want to point out here is that they do use that time behavior, so they treat it like a signal. If I look at maybe the key page of the architecture, so these log entries that they're showing are saying what are the kind of categorical events, and they make a key from that. But they also measure how long it takes between each events, and they're kind of stashing aside these T1 minus T0, T2 minus T1, T3 minus T2, so that they have essentially a kind of time series or a wave form of the things that are being the trace. And so the log gets parsed, it goes into this anomaly detection that we've looked at, and in the end, they wind up looking at a sort of secondary search to say, let's look at these time delays. They actually, if they think there's an anomaly, they're going to ask a human to say, is it really? In which case, we'll do something about it, but we may say if it's a false positive, then we actually kind of go back into the training space and try to adjust the model. Okay, so let's think a little bit about weaknesses and attacks on machine learning. So probably the biggest thing, and one of the reasons why it hasn't taken over the world yet, is that computing is really variable. The programs are changing all the time.
It's better if you can somehow separate the processes that are running on the machine into like, this is doing only one kind of thing so that it's less random. So there's a trend called containerization that basically does just that. It sort of freezes a snapshot of the operating system and the software and the data. Docker is the first one that I heard about, and maybe the most famous one. So if you're running on Amazon, you spin up Docker and you get a log just for some very dedicated process. Another thing is that is this idea of obfuscation. So a malware may attempt to hide itself by decompressing things on the fly. Everything looks kind of similar when it's compressed. You can try to poison the training data and models. You can actually use machine learning yourself and make sure that you're not detected. There's some famous papers about how to fool deep learning. There's a thing called GAN networks that co-trains an attack and a defense at the same time. I have a picture of this here, but we're sort of coming to the end. Basically, what you try to do is you generate something, in this case, an image that's fake, and then you have your real training data, and you try to make both of these colored boxes get better. So you want to be able to train to detect real from fake, but you also want to train the generator to make more convincing fakes. So if we say that the attack is in the image box up there, then so if you're a black hat attacker, you basically could use this kind of technique to make sure that you're classified as fake. So in summary, machine learning has the potential to recognize changing attacks and unusual behavior better than the kind of signatures, the crypto hashes that have done a lot of work, just say like on malware detection. But it can also be used by attackers. So part of why it's hard is computing a network is really variable, which makes it hard to learn. So if you can, you want to reduce the variability. Really, you probably require expert tuning to get the job done right, or you're going to have the false positive problem with just too many alarms. And if you can actually look at the time and space relationships between things in a log, kind of unclear on what space means in this context, but this is better than just data. Okay, so here I'm just going to throw this screen up that has more resources, and I think at this point I can take questions.
So we don't have any questions posted at the moment in chat, David, but I did want to ask you, about halfway through the presentation, you were talking about adaptive feature discovery because there's too many features that were manually built in, and adaptive feature discovery was probably a better alternative. So can you provide an example of how that works?
Yeah, I'm going to go back to the picture of deep learning. This is, I threw out a slide that had maybe a slightly bigger description, but so generally when you have, let's talk about images, these so-called feature maps is really taking a little array that's called a kernel with different numbers that are somehow generated systematically, and you go around and you multiply it by a little window in the data. So it's like a sliding window. And if some particular set of numbers in there happens to match what is in the window, we will say that that's given me a good response. So I am seeing this kind of patch is what people will call it in the data. And then when you do the training process and set weights on a network, which we didn't dive into too much, basically if you see it, then you're going to set those weights to handle that kind of data. If it turns out that one of these convolution kernels or little image processing matchers doesn't ever get seen in the data, then that's just going to kind of wither away. And in some network architectures, they will actually like trim those out. Something that I didn't really say is that in these deep learning models, they literally will have like millions of those little
nodes and connections. And that's why you have to throw them at, say, a GPU for, at least 24 hours or something typically, but sometimes much longer. And now people will try to throw these to essentially GPU server farms to do the training. It's believed by neuroscientists that this is also the way our brains work, is that they really find a lot of structure out there in the world. And we basically sort of focus in on combinations of sort of orientations and sizes at different scales that are actually present in the images that we see. I don't know if that's a great description, but it's kind of I'm sure that you could take like a whole semester class in adaptive feature.
That's actually a really good description and a great segue too. So as you're speaking of neurosciences, one of the things that I find captivating in your presentation is how humanistic machine learning is. A lot of it seems to be related to human learning. And something that you said towards the end was that it's hard to model because computing is variable.
Yeah.
Is it as difficult to model as, let's say, human learning, since it appears to be so humanistic?
Well, first of all, that's kind of controversial. Like, I think the sort of business level hype and a lot of the sort of engineers and practitioners will claim that this deep learning is really starting to look like what's going on in the brain, but there are reasons to believe that that's not true, both from the architectural standpoint and from the sort of quality of results standpoint, because one thing that people know is that humans learn categories like, I don't know, dogs, cats, hot dogs, and learn language based on relatively little exposure to data. So there is a field in machine learning called one-shot learning, which basically says, instead of looking at a million pictures of a dog and a million pictures of a cat, it would be much better if you could look at one, or I'll give you a little break and say you can look at 10, and then you could recognize all the dogs and the cats in the world, because a human is actually able to do that pretty well, right? So, but then what a human isn't able to do is look at a log file.
Okay, yeah.
So when the data is kind of random looking and confusing, machines are our friends. And I think a point I wanted to make at the end is I don't think this stuff is going to be automated anytime soon. There are going to be humans in the loop. And what your sort of best hope is to sort of handle the fire hose of data, potential alarms, and, try to sort of manage what you actually have to look at.
Okay. I do have a couple of questions that have popped up in chat. One of them is from Owen McNally, and he's asking, do you categorize machine learning as a branch or subcategory of artificial intelligence, or a field that overlaps with it?
It's, I wouldn't like to say that either one of those is completely wrong. It's, if you say you're an AI expert and you don't know anything about machine learning, that's a bit strange these days. But there is a lot of AI work that historically has not always relied on machine learning, but there are relatively fewer papers being published in that world all the time, I think. But it's not to say there's nothing interesting going on. But for example, artificial intelligence often used to deal with planning, like, okay, I have a robot and it needs to plan how to get around an obstacle course. That was, for a long time, not really something that people were doing with machine learning, but now I think there are probably 90% of that work is machine learning. Okay.
Okay, so we have one last question, comment, and this came from Jeff as you were talking about giving the explanation of adaptive feature discovery. He said, so attackers are trying to add noise to the detection system to match actual signals. Is that what you were saying, or part of what you were talking about?
It's certainly something that could be done. Like, for example, if you if you know that somebody is using a machine algorithm and sort of treating their data as something to be learned, in fact, you can make it more difficult to learn by making it more noisy, or machine learning people will say making it higher variance, right? So to the extent that you can make things look kind of like not completely weird, but more random, that is a way to make machine learning more difficult.
Okay.
Hope that makes sense. Yeah.
One last question really quick here, because I think this applies to what a lot of the folks that have joined us today are interested in. This is from ML. Can you talk a little bit about some application of machine learning and image processing in the cybersecurity field? For example, facial recognition as a screening mechanism, how to detect stenography, etc., or is it still in its early stage?
No, I would not say that's in its early stages. It is, things are getting to be pretty strong, and people are scaling that up to be able to work at ever larger pools of images. I think we probably have all heard about, like, in China in particular, they're really moving pretty fast on that front. And there are also known ways to attack that. Just in image recognition in general, I vaguely mentioned something, but if you do a search for fooling deep learning, you'll find some papers and pictures where basically people go in and they just kind of, it's a little bit like this generative adversarial thing. They say, like, can I find something that that defeats the deep learning network by gradually maybe using a genetic algorithm to search the space of possible images and say, oh, so not only is this thing guessing wrong, it has like 99% confidence that it is a penguin. And the kind of shocking thing is that often these things just look like white noise. There is no way that a human would ever confuse these things. So while it's out there, there are ways to defeat a lot of the learning algorithms, but it's a very active research field. And I think right now in face recognition, it's like the algorithms are kind of winning, and maybe if you don't want to get detected, you have to wear a mask or glasses, or scrunch your face up, or paint one of those Maya native masks, or and change it every day, project random patterns onto your face.
I've got a mind mask hanging on my wall in front of me. You just made me think of that. Maybe I ought to put it on now for an effect, right?
Yeah, there you go.
Okay, so that's about all the time we have today. David, do you have any closing comments?
Well, I just will go back to I bounced out. Yeah, I just was going to give my contact, David L. DeMaris at gmail.com.
Okay, that's awesome. And so we definitely appreciate you sharing this with us today. It's fascinating information. And just so everybody knows, there will be a recording of the webcast today that'll be available on the National CyberWatch website and also on our YouTube channel in the coming days. So keep an eye out for that. Thanks everyone for joining us. Keep an eye on your inbox for announcements about upcoming webcasts. And again, thanks for tuning in, and we look forward to seeing everyone again soon. Thank you, David. Thank you, everybody in attendance.